Just take a look around you right now. Your watch, your thermostat, maybe even your TV. They're all part of this massive, connected world. But what happens when that entire world gets turned against us? How do you even begin to defend our smart homes, cities, and industries from a cyber threat that could shut everything down?
We're not just talking about a few gadgets here. We're talking about billions, literally billions, of devices that make up the Internet of Things, or IoT. From the smart speaker in your kitchen to mission-critical sensors in a factory, they're all part of this huge interconnected web. And frankly, that makes them a massive and really tempting target for cyber attacks.
So with all these devices chattering away, sending data back and forth, what's the single biggest threat out there? What's the one thing that could bring this entire smart ecosystem to a grinding halt?
Well, it's something called a DDoS attack. That stands for Distributed Denial of Service. The easiest way to think about it is like a digital mob blocking the entrance to a store. But in this case, hackers aren't using their own computers. They create what's called a botnet, where they secretly hijack thousands of everyday IoT devices and then use their combined power to flood a target with so much traffic that it just gives up. It gets completely overwhelmed and shuts down.
And that brings us right to the heart of the problem, what we're calling the smart device dilemma. Because protecting these things is obviously crucial, but as you're about to see, it is way harder than it sounds.
To really get why, we need to look at how this whole system is built. So at the very bottom, you've got the IoT layer. That's all the billions of devices themselves collecting data. In the middle, you have what's called the fog layer. You can think of these as local mini data centers or gateways. They process information super fast without having to send it all the way to the cloud. And then at the very top, you have the cloud with its practically infinite processing power. Okay, and here's the dilemma. Our absolute best weapons against these attacks are powerful deep learning AI models. But the thing is, they are total resource hogs. They need the kind of raw computing power you can only find in the cloud. They're just too big, too slow, and too clunky to run on those smaller, faster devices in the fog layer, which is exactly where we need the protection to be.
So our defenses are essentially stuck. They're stuck in the fog. And this is where that real conflict between raw power and lightning speed really comes into focus. It all comes down to this fundamental trade-off. On one side, you have the cloud. It has massive power, which means really high accuracy. But it's slow. The data has to travel a long way, which gives it high latency. On the other side, you have the fog. It's incredibly fast because it's local. That's low latency, but it just doesn't have the processing muscle. So the big question is, how on earth do we get the brains of the cloud to operate at the speed of the fog? And that's the exact puzzle researchers set out to solve. How do you possibly squeeze all that power from the cloud into the nimble but very limited fog layer? How do you make your frontline defenses both incredibly smart and incredibly fast? The solution they came up with is just so elegant. It's all based on this simple yet really powerful analogy: a teacher and a student. The technique is called knowledge distillation, and the idea is just brilliant. You take a huge, complex, super knowledgeable AI model, that's the teacher, and you have it teach a much smaller, more efficient model, the student, everything it knows. The student doesn't just memorize the answers, though. It actually learns the teacher's entire decision-making process.
So, let's meet our teacher. This thing is a massive AI model. It lives up in the cloud, where it has access to all the computing power it could ever want. It spends its time just poring over these huge data sets of DDoS attacks, learning to spot every subtle variation, and basically becoming a world-class expert on the subject. And then we have our student. This model's pretty much the exact opposite. It's designed from the ground up to be lightweight, nimble, and incredibly efficient. It's purpose-built to run on that low-power hardware that you find in the fog layer, right there on the front lines. So, how exactly does this all work? How does the student actually learn from the teacher? Well, it's a really fascinating process that ends up creating this intelligent digital security guard. It all happens in two main phases. First up is the offline phase. Back in the cloud, the teacher model trains and trains, becoming an absolute expert at spotting these attacks. Then comes the knowledge distillation. The teacher takes all of its complex knowledge and basically boils it down to the most essential rules and patterns, and then it teaches those to the student. After the student graduates, we move to the online phase. This compact, lightweight student model gets deployed out into the real world, onto those fog nodes, and from there, it uses all that distilled wisdom to watch the network traffic in real time, instantly spotting and flagging DDoS attacks the moment they start.
All right, so here's the big question. Did it actually work? I mean, after all that training, how did our student model do on its final exam? Let's take a look at the results. The results were, frankly, staggering. This lightweight student model, running on simple, low-power hardware, was able to detect DDoS attacks with over 99% accuracy. It learned its lessons perfectly. And this chart is where you see the true genius of this whole idea. Look at the accuracy. It's practically identical. The student is just as smart as its teacher. But now look at the speed. It's not even a contest. The student model is exponentially faster, detecting threats with just a tiny, tiny fraction of the delay. So what this really means is that we got the best of both worlds. We have the elite, top-tier accuracy of a massive cloud-based AI, but it's all packed into a tiny little footprint that's fast enough to be deployed right on the ground in the real world. So what does this all mean for the future? Well, this goes way beyond just stopping one type of cyber attack. This is really a blueprint for building much smarter security for tomorrow. So why is this such a big deal? Well, for one, it finally bridges that huge gap between powerful AI theory and practical, real-world security. It gives us a way to put intelligent defenses right where we need them most, even on low-power devices. This teacher-student model is totally scalable, which means we could use it for all kinds of other applications in the future. Oh, and there's a really nice bonus. Because it analyzes data locally, it actually enhances privacy, since less of your sensitive information ever has to leave your local network.
What this research really proves is that we can effectively teach our small, everyday devices to defend themselves with incredible intelligence. And that leaves us with one last, really exciting question to think about. If we can teach our devices to be this secure, what else can we teach them?